In this video, I'm going to go through the 2019 Unit 3 paper, which is the Practical Booklet B. Question 1. In this question, you have to describe how to prepare a burette and then fill the burette. And then obviously you can see from the second bullet point, then you have to describe how the accuracy is ensured. Now, anytime you prepare a burette and indeed prepare a pipette, there are some general things that apply to both. You'd first of all rinse it with the ionized water. You then rinse it with the solution that you're going to put into it, which in this case is sulfuric acid, and then you fill it with that solution. So to start off with, I'm going to write down that we'll rinse it with distilled or deionized water. And then I'm going to rinse the burette with the sulfuric acid and name the solution that you're putting into it. Next, I'm going to fill the burette with the sulfuric acid. And I'm going to do that until the bottom of the meniscus is on the 0.0 mark. And when you're taking readings, you've got to read from the bottom of the meniscus. And then onto accuracy when determining the endpoint. The first thing you can say is that you're going to read the volumes from the bottom of the meniscus. And you're going to add dropwise near the endpoint. And finally, make mention that you're going to swirl the flask. So those would be enough points that would ensure that you would get the full marks for this question. Laying it out in this format where it's bullet points makes it nice and clear for the examiner to see your work. And it makes it easier for that examiner to mark your work. Just want to highlight one thing. I've used the word rinse here, so rinse the burette. Same would apply to the pipette, where you'd rinse the pipette. Do not say wash the burette. Okay, so we're not washing the whole thing, we're just rinsing the inside of it. On to part B then. Why is a rough titration carried out? Well, that just allows you to estimate the endpoint, or it allows for faster subsequent titrations. If you didn't do a rough titration, you wouldn't know what volume was going to be required for the two solutions to react exactly with each other. And so you'd have to add it drop by drop, and it would take you a long time to carry out the titration. So why is a rough titration carried out? It estimates the endpoint or allows faster subsequent titrations. Part 2 then, we'll have to state the colour change at the endpoint. So I've included the introduction to the question here. So 25.0 cubic centimetres of the sodium hydroxide solution in the conical flask. So it's going to be here. This is the alkali. That means then that the acid is going to be in the burette. The indicator being used is methyl orange, and methyl orange is yellow in alkali. So it's going to start off yellow here, and then when the acid is added, it's going to turn red. Part 3, then calculate the number of moles of sulfuric acid added from the burette. Well, to work out the number of moles, we need concentration and the volume used. The concentration is given to us here. Again, this is copied from the start of the question. So it's going to be 0.045. And from the previous part of the question, the titer was 20.1 centimetres cubed. So we're going to multiply the 0.045 by 20.1, dividing that by 1,000, and that equals 9.05 times 10 to the minus 4. Part 4, calculate the number of moles of sodium hydroxide present. Well, when you see the equation like this, you should know that this means you have to use the ratios. You've just worked out that you've got 9.05 times 10 to the minus 4 moles of sulfuric acid. That means it's going to react with twice the number of moles of sodium hydroxide. So the answer here is 1.81 times 10 to the minus 3, or you can have 0.00181. Make sure that your number of moles here is at least to two significant figures. So don't just do 0.002. Okay, that would be wrong. Part 5, calculate the concentration of the sodium hydroxide. Well, concentration equals the moles divided by the volume. So in this case, it's going to be 1.81 times 10 to the minus 3. The volume was 25.0 cubic centimetres, and then it's going to be multiplied by 1,000, and that gives an answer of 0.072 moles per cubic decimetre. Now, another way of doing this is if we go back up to part 4, this number of moles is present in 25 cubic centimetres. The concentration down here is moles per cubic decimetre, and a cubic decimetre is 1,000 cubic centimetres. To go from 25 to 1,000, we're multiplying by 40. Therefore, we could just simply multiply this number of moles by 40, and that would obviously give us the same answer here, 0.072. And then part 6, we'll have to convert the concentration from moles per cubic decimetre to grams per cubic decimetre. So here is the value from the previous part of the question. And to work out the mass in grams, we're going to do moles equals mass over RFM and rearrange this equation to give us the mass. So the mass is going to be the moles times the RFM. Well, the RFM of sodium hydroxide is 40. So this is going to be 0.072. That's how many moles there are in a cubic decimetre, times the RFM, and that works out to be 2.88 grams per cubic decimetre. Next question then. This is an ionic compound, labelled A, and we've got some tests. So I'm just going to go through each of these. Test 1, we've got 5 cubic centimetres of a few drops of sodium hydroxide solution. So right away I know I'm testing for a metal ion. The white precipitate means that it could be aluminium, zinc, or magnesium ions present. Remember, this here is testing for metal ions. Not just the metal, it's the metal ions. So it doesn't actually identify which of those ions it is. So we need to go on and look at some more. Number 2, or test 2, the sodium hydroxide solution is added in excess. And here the white precipitate, which was formed initially, dissolves. So it is soluble and it forms a colourless solution. Well, that means that it's either a solution containing zinc ions or aluminium ions. It's not magnesium ions because the precipitate that forms in the solution containing magnesium ions remains. It's not soluble. So that rules that one out. Okay, I'll just go on to test 3. This time, a few drops of silver nitrate solution are being added. Well, that's testing for a halide. Anytime you see silver nitrate solution, your mind should automatically be thinking this is a test for a halide. Chloride, bromide, iodide. The fact that it's cream identifies it as being a bromide. Test 4. This time, a few drops of ammonia solution are being added, and we get a white precipitate. Now, this initially produces the same result as sodium hydroxide solution. So this here again tells us that it could be zinc, aluminium, or magnesium ions. Now, of course, we know from test 2 that it's either zinc or aluminium ions. So this is where test 5 comes in. The ammonia solution is now added in excess, and the white precipitate is soluble. That means that the solution contains zinc ions, because the white precipitate that forms with aluminium ions remains insoluble when excess ammonia solution is added. The solution with zinc ions is the only one which would involve the white precipitate dissolving. So So now we know it contains zinc ions. So on to the actual question then. Write the formula of the cation. Well, the cation is the metal ion. That's going to be Zn2+. And we have to write the formula. And then part 2, write the formula of the anion. Well, we know that's a bromide, so it's going to be Br-. Part 3, write the name and formula of the ionic compound. Okay, well, we've just worked out that it contains zinc and bromide ions, so that is going to be zinc bromide with the formula ZnBr2. Write an ionic equation for the reaction in test 3 with or including state symbols. I've included test 3 here. This is the one with silver nitrate solution and the cream precipitate. Well, the part of silver nitrate solution that tests for the halide is Ag+. So it's going to be Ag+, and that's dissolved in the solution. So it's AQ. That reacts with the bromide ions, and we know it's bromide ion because of the cream precipitate. So it's going to be plus Br-. Again, these are in solution, so it's aqueous. But when these two react together, it forms an insoluble solid. That's the precipitate. And that's going to be AgBr, and we put in an S to indicate it's a solid. Part 5, name the white precipitate formed in test 4. Well, we know it's a solution of zinc ions. Okay, we've worked that out and established that. So that means that the precipitate is zinc hydroxide. Anytime you add ammonia solution, a few drops of ammonia solution or a few drops of sodium hydroxide solution, the precipitate that forms is always a metal hydroxide. So in this case here, we know it's a solution containing zinc ions. The precipitate is zinc hydroxide. Okay, on to B, part 1. How could you prove that the solid contained potassium ions? Oh, for this one, you just carry out a flame test. You don't need to give any details of that. There are only 2 marks for it. So just say a flame test, and of course potassium will produce a lilac flame. And part 2, describe the procedure you'd use to prove that the solid contained carbonate ions. Well, we can test for carbonate ions by adding an acid, something like hydrochloric acid, and that will cause fizzing. Now, there are 4 marks for this question, so you're going to have to give a bit more detail. The gas that's produced is carbon dioxide. Always associate carbonates with carbon dioxide, and it can be tested by bubbling into lime water, and it'll change from colourless to milky. On to question 3. So here I've put the start of question 3, showing the graph beside part A. So here we have to draw a labelled diagram of the assembled apparatus. Now notice it's assembled, so don't be drawing separate pieces of apparatus. So you read through the question and pick out the key pieces of equipment. So we've got the marble chip, it's added to the acid, and it's in a conical flask. So I'm going to draw a conical flask. And then we're told the mass of the flask and its contents were recorded. So that means it's sitting on an electronic balance. I'm just going to go back up here. It says the marble chip was added to the hydrochloric acid, and these are in the conical flask. So you need to show those in here. And then the last thing that we need is a stop clock or a stopwatch, because the mass was recorded every 10 seconds. So just draw some sort of, again, thing like this to indicate a stopwatch or stop clock. Now it has to be labelled. If you don't have any labels, you'll get no marks. And there we get our full 4 marks for this question. Be careful here when you're labelling the balance. Don't say scales. Okay, so they're not scales, it's an electronic balance. B, part 1. Explain why the graph levelled off. You can see that here. That just means that no more gas is produced, or the reaction stops. Part 2. The experiment was repeated at 40 degrees C. And I have to sketch the graph that we would expect to obtain. Okay, so 40 degrees C, originally it was 25 degrees C. Increasing the temperature, we're going to increase the rate of reaction. It's going to start at the same place as the original, so 101.70. It's going to have a steeper gradient. It's going to be lower than the original, but it's going to level off at the same place. See part 1. Have to use the graph to calculate the mass of carbon dioxide produced. Well, we'll start off at 101.70 and we finish here, which is 101.48. So you just find the difference between those two. That's 0.22 grams. Don't forget your units. Part 2, calculate the number of moles of carbon dioxide produced. Well, we've just worked out that there are 0.22 grams of it. We divide that by the RFM, which is 44, and that works out to be 0.005 moles. Part 3, we have to use the answer to see part 2, which is the number of moles of carbon dioxide, and the balanced assembly equation to calculate the number of moles of calcium carbonate. So if we go back up to the top for this equation, we can see that the ratio of carbon dioxide to calcium carbonate is 1 to 1. So there's going to be the same number of moles of calcium carbonate, 0.005. Part 4, calculate the mass of calcium carbonate. Well, from the previous question, we'd worked out that there were 0.005 moles of it. The RFM of calcium carbonate is 100. So we multiply the moles by the RFM, and that works out to be 0.5 grams. On to part 5. The mass of the marble chip was 0.56. Calculate the percentage of the calcium carbonate in the chip. Well, all we do here is we just simply divide the mass of the calcium carbonate that we've worked out here. So that's 0.5, and we divide that by the total mass of the marble chip, which is 0.56. It's a percentage. We're going to multiply it by 100, and that works out to be 89.3%. Question 4 is about the reactivity of metals. So A part 1 is telling us to complete the table. So here we just simply have to work out the temperature change. So this should be straightforward. The first one for magnesium is going to be 19, and then it's going to be 3, and obviously 1 for tin. Part 2, the reactivity for 4 of the metals is given. Place tin in the reactivity series. Well, this is where we're using the temperature change to work this out. Magnesium is the most reactive because it has the greatest temperature change. Zinc had the next highest one, which is why it's second after the magnesium. You can see that iron is going to be next, and copper, which didn't change the temperature at all, is down at the bottom. Now tin is just above copper, but below iron. So I'm going to put tin in here. Part 3, explain how the data in the table shows the reaction of magnesium and the nitric acid is exothermic. Well, in exothermic reactions, the temperature increases. That's the answer. 2 factors which should be kept the same during the experiments. This is where we're adding the pieces of metal to the acid. So we're going to be things like same volume of acid, the same concentration of acid, the same particle size or the same surface area. And you could also have the moles of metal. Now it's better to say moles of metal than the same mass of metal, because you could have, say, 1 gram of each of the metals, but that will obviously be a different number of moles in each case, and moles is just the number of particles. So if we want to make this a fair test, we have to make sure that we're reacting the same number of particles with the acid in each case. So that's why it's moles of metal rather than mass of metal. Part 5 then, write an equation for the reaction of magnesium with nitric acid. Well, magnesium is Mg, nitric is HNO3. That goes to give magnesium nitrate and hydrogen. And to balance it, need to put a 2 in front of the nitric acid. Part B. So we're going to use this table, which shows the reactions of chromium and cobalt, and then use the information to answer part 1. So let's look at the first bit. Cobalt is more reactive than chromium. So is that true or false? Well, if I look at cobalt and its reaction with chromium-3 nitrate, there's an X here, so that means that chromium is not able to react with the chromium-3 nitrate, so it's less reactive than chromium. So this one here is wrong. The second one, cobalt is more reactive than copper and tin. So again, if I go to cobalt and I look for the reaction between cobalt and a copper solution, which is here, there's a tick. That means that cobalt is more reactive than copper. And the other one was with tin. Again, there's a tick here, so that means cobalt is more reactive than tin. Put a tick in that box. And then the final statement, chromium is more reactive than iron. Okay, well, we'll do that one first. So we'll look at chromium and its reaction with an iron solution, which is here. And you can see there's a tick, so that means that chromium is more reactive than iron. Now, the second part of this statement is that chromium is less reactive than zinc. Okay, so again, chromium is going to react with a zinc solution, so zinc nitrate. There's an X, so that means that chromium is less reactive than zinc. So this statement is correct. Part 2, name 2 products of the reaction between cobalt and copper-2 nitrate. Well, the cobalt replaces the copper here, and so you're going to end up with cobalt nitrate and copper. To be careful here, do not write copper 2, because when you write it like that, that means copper 2 ions. But they're not ions anymore. The copper ions get turned into copper atoms. And then the final part here is a balancing equation for the reaction of chromium with iron 2 nitrate. Or chromium is just Cr. Iron 2 nitrate. Then you get chromium 3 nitrate. And iron is produced. Obviously it needs to be balanced. So we've got a 2 here and a 3 here. Well, both of those will go into 6. So 3, 2. But now that has generated 2 chromiums on the right, so we need 2 on the left. 3 irons on the left, 3 irons on the right are needed. Question 5. So A part 1. State the functional group present in compound B. Okay, so let's look at compound B. Mix the liquid with bromine water and shake. The bromine water remains orange. Okay, so that is a test for the carbon-carbon double bond, so it's not an alkene. We mix it with acidified potassium dichromate, and it's warmed and it changes from orange to green. So that means that it must be an alcohol, because alcohols get oxidized to the carboxylic acid. The functional group, therefore, that it contains is OH, or you can write hydroxyl. Don't say alcohol, that's the name of the compound. The functional group is hydroxyl. To what homologous series does it belong? Alcohols. Part 3, state the functional group which is not present in B based on test 1. Well, I've already mentioned this. Up here, bromine water is a test for a C double bond C. It doesn't change in this case, so that means that it does not contain that carbon-carbon double bond. Part 4, the functional group which is not present in B based on test 3. Well, you can see here in test 3, sodium carbonate is added to it. There's no reaction. That means it's not an acid. And the acids in organic chemistry are carboxylic acids. And they have the functional group COOH, or you can call that carboxyl group. So if you add sodium carbonate to a carboxylic acid, there will be fizzing. So in this instance, there is no reaction, so that means it's not a carboxylic acid. Next part, compound B, which we know is an alcohol, it contains 3 carbon atoms. Draw the structure formula of the compounds it could be. So I'll just draw 3 carbon atoms. It is an alcohol, that means it contains the OH group. So I'll just put it on here. And then the rest of the molecule has to be surrounded with hydrogens. And the name of this one is propan-1-ol. The second one, all I have to do is move the OH group to a different carbon. Now there's no point moving it over to this carbon because that would be exactly the same as this one. Just turn the molecule around. Also, there's no point moving the OH to here or to here because that is still the same as propan-1-ol. The OH would still be attached to the same carbon. So I need to move it into here. And that makes propan-2-ol. Make sure you've got your hyphens in here, and also be careful of where you draw the bond. This bond has to be going to the O. B part 1, what is meant by the term weak acid? It partially ionizes or partially dissociates in water, or you could say in solution. Part 2, describe how you would test samples of hydrochloric and ethanoic acid to prove that one is weak and one is strong. Well, you could just use a pH meter here, and the strong acid will be 0 to 2 and the weak acid would be above 2. I'm putting in an upper limit here of 6 because if you just write above 2, well then that could indicate it's 8, 9, 10, etc. And obviously it's not. It's in the range 3 to 6. You could also say you use pH paper or universal indicator paper. The strong acid will be red and the weak acid would go orange or yellow. Okay, on to the final part of the paper. Name the salt produced in the reaction of propanoic acid with sodium hydroxide. Well, you get sodium propanoate. Anytime a carboxylic acid reacts, which is what this is, it changes the ending of its name to OAC. So ethanoic becomes ethanoate, methanoic becomes methanoate. So here propanoic becomes propanoate. Suggest a colour change observed when copper 2 carbonate is added to propanoic acid. Well, the acids themselves are colourless. You end up with copper 2 propanoate, and copper solutions are usually blue. Finally then, we'll have to write a balanced equation for this reaction. Copper 2 carbonate, remember that's a green solid, so CuCO3, propanoic acid, or you could write it as C2H5COOH. That goes to give then copper propanoate. So that is propanoate, and this whole thing has a valency of 1. The copper is copper 2, so it has a valency of 2. And you put brackets around that and leave it like that. Now you can put the copper first, and so if you write it this way, that's perfectly fine, but we tend to write it this way. Again, you can use this if you prefer. So now I'm just going to continue with this top one. An acid plus a carbonate gives a salt. Well, this is the salt, plus water, plus carbon dioxide. It has to be balanced, and you can see that there are 2 propanoates here. So we're going to need 2 propan OH over here. That's it, balanced.